Hi guys, it's Kate, and this is the second video for week 8 of Math 23B. We introduced differential forms earlier, and we got that computation under control. You'll get a lot of practice with that in lecture this week, as well as in your small group problems and in your homework. And I know you have burning questions inside of you. Why do we use these? When do we use these? Try to hold off for just a few more lectures until we get some more tools in our toolbox, and then we can start combining them and you'll see the use of differential forms. We're going to introduce two new topics, well, 1.5 new topics, vector fields and form fields. Remember that a vector field is a function that assigns a vector to every point in Rn. It maps from Rn to Rn. So it's very easy to draw a diagram that represents a vector field. Here's a great one right here. Now there's also such a thing as a form field, which maps from Rn to, remember that this is the space of all k-forms on Rn. And so what it does, it assigns a k-form to every point. And it's usually written in terms of basis k-forms. So for instance, phi here is an example, and you can see that depending on where you are in space, you will have a slightly different form here at every single point, because the coefficients, note that there's z here, y here, x here, the coefficients on those basis k-forms change depending on where you are. Unfortunately, there's no way to represent a form field like we did with a vector field up here, but it's useful to at least have one written out for you. Now, as we're looking at differential forms and thinking about what they do, sometimes it's more useful, instead of thinking of k-forms as taking an ordered pair of vectors as its argument, we can actually think of these k-forms as taking a single argument, which is the k-parallelogram spanned by the vectors that we used to consider as individuals. So instead of thinking of phi acting on v and w separately, we can think of phi acting on the parallelogram spanned by v and w. So that makes sense that if phi acting on v and w was equal to negative phi acting on w and v, note that there is this notion where if you swap the order here, you're going to get a factor of -1 incorporated into this expression. It must be the case that if phi is acting on the parallelogram spanned by v and w, it will be equal to -1 times phi acting on the parallelogram spanned by the vectors in the opposite order. Now for a form field, the coefficients of the basis forms are functions of position, right? Up here, dependent on where you were in space, what z, what y, what x was there. And so a form field is a function both of its anchor point, where you are in space, generally a differentiable but nonlinear function, and of one or more spanning vectors. So not only do you have where are you in space, that's going to give you z, y, and x, but it's also dependent on v and w, which are going to create the parallelogram that it acts on. So we combine the anchor point and the spanning vectors to form an anchored k-parallelogram. So you can think about two vectors v and w, and then their anchor point is right here. And all three of those things, the location of that anchor point, as well as the two other vectors, contribute to the value of the form field. So that's how you want to think about them when you're dealing with form fields. Not only do they depend on where you are in space, but they also depend on the k-parallelogram that's anchored at that point. So let's take a look at this. It says that U is a subset of Rk. It's a bounded open set of parameter space whose boundary has k-dimensional volume 0. The C1 mapping that takes us from U to Rn, that's called gamma. That's our parameterization. It determines a parameterized domain. A point in the parameter space is mapped into an anchored parallelogram. Note that there's actually a point in the parameter space that maps into the anchor point for the parallelogram, and then the vectors that span the parallelogram come from the columns of the Jacobian of our parameterization. The anchor point is going to be gamma u, and the parallelogram is spanned by the k columns of the Jacobian matrix. We do not require that gamma u be a manifold. Why is this so useful? Well, quite frankly, we really need a way to describe these anchored k-parallelograms. Same as when we want to go about integrating over manifolds, we need parameterizations to describe that manifold. When we want to start playing around with form fields, in a particular subset of RK, we need to be able to describe that subset, and then we need to be able to describe those parallelograms, not just where they're anchored, but also the vectors that span them, all in the same language, and that's why parameterizations come in handy here. It should not come as a surprise that our next topic is going to be how to integrate a form field over a parameterized domain. I suppose I kind of let that hint go in the last couple seconds on the previous slide. But of course, if you're hoping to integrate a K-form field over a parameterized domain, that's gamma of u, what you actually want to do is integrate in the parameter space and then describe all the particular parts of what phi is acting on, right? The parallelogram that is anchored at gamma of u, that's a point that gamma of u maps from the parameter space to the actual point where that parallelogram is anchored in the original space, and the parallelogram is spanned by the columns of the Jacobian matrix of the parameterization. So just like you have a choice of how to compute a particular integral, what we're doing here is we're putting everything in terms of the parameterization. We take that K form and we're actually computing it on a variety of parallelograms anchored at various points over the entire subset U. And then, of course, using the parameterization, we can also find the vectors that span the parallelogram as well. We're basically breaking up U into dyadic cubes. We map each into a little K parallelogram by using gamma of U, and then evaluate the K form on those parallelograms, and then sum the results. We will go through plenty of examples of computing these types of form fields and their integrals over parameterized domains in class. Now, let's see what we can sort of toy around with as far as vector fields go. Given any vector field f, we can define a one-form field, which is called the work form. Its notation looks like this, and what it really is the dot product between the vector field and some vector v. For k equals 1, a parameterized domain is just going to be a curve, right, a one-dimensional manifold. To each anchor point is attached a one parallelogram spanned by a single vector, and the integral of this guy right here, which is basically saying how much does the path point in the same direction as the vector field. Well, that integral is going to give the work form over an oriented curve, which is equal to the work done by the vector field on a particle that moves along this curve. So that is the significance of the work form. If we have a vector field, we can define a one-form field, which is called the work form, that does this, that if we integrate it along this curve, it will tell us the force done on the particle to move it along the curve. And this actually shows up in thermodynamics quite often. In thermodynamics, a parameterized domain is basically a succession of equilibrium states through which a gas passes. And the parameterization function specifies the volume and pressure of the gas as a function of a parameter. So here is how volume and pressure interact, or really I should say relate to each other with respect to this underlying parameter U. And this describes the isothermal expansion of a gas, because that's going to be with PV, the product of pressure and volume, equaling 32. Now in this case, there are a lot of one-forms at work. There are basis one-forms, dV and dP, and then there are also one-forms of physical importance. So here's an example of a one form right here, 5/2 p dV plus 3/2 v dP. I mean, that's a linear combination of basis one forms, but it is a one form too, which determines the heat absorbed by the gas. And then there's also this one form, p dV, which determines the work performed by the gas as it expands. So these one forms, when you compute them, actually give you values of very great physical significance in this particular example. Now, if you take the integral of this first one form, the one that determines the heat absorbed by the gas, and you integrate it over the parameterized domain, it actually gives you the total heat absorbed by the expanding gas. And in this case, this is not the work form of any vector field, and there's no concept of length or dot product in the PV plane. So this is a great example where one forms have great physical significance. Even though the plane itself, it doesn't represent a physical description of the space as far as Euclidean distance or things like that. There's no length, there's no dot product, there's no angle significance in the PV plane, and yet these one forms integrating over various parameterized curves can really tell you a lot about the physical characteristics of a particular situation. We will do several examples involving this application as well, thermodynamics, but there will be tons of these throughout the semester, or remainder of the semester. It's running out quickly. But this is just the tip of the iceberg. These are some excellent physical applications of one forms and what they can do. But the key for this week is to understand what differential forms are. Really, how to compute them would be the most reasonable answer to that. We're going to build on what they are and what their significance is. Understand how to build and interpret form fields, which not only depend on your location in space, but also the vectors that span a particular parallelogram at that point. And then last but not least, the beginnings of using these one forms and their integrals over particular parametrized domains. So integrating work forms and what does that mean in a physical sense, depending on the situation that you've described using your parametrization as well as your vector field. So enjoy this week. It's definitely a change of pace. We're building towards a big finish with the fundamental theorem of calculus. And as always, if you have any questions, don't hesitate to ask.